Okay, in our last video, we introduced the concept of implicit differentiation, and we want to continue working with that and some more examples in this video. And let's start off with, suppose we have a product. Let's just make it simple to begin with. Suppose we have x times y, say, equals 1. And we want to solve this for dy dx. Now again, we can get an explicit value for y. We can say, well, y is equal to x to the minus 1. So dy dx that would be equal to minus x to the minus 1, which is minus 2, or that would be equal to minus 1 over x squared. And that is correct. What we want to do, though, is, as we did in the last video, solve this for dy dx using our method of implicit differentiation. And here we have a product of two variables. So it's going to be y times this derivative, and we're taking derivatives now with respect to x. So it's y times dx plus x times this derivative, which is dy dx, and that will equal the derivative of 1. Of course, that's just a constant, so that is 0, and dx, that's just 1. And we can take the y over to this side of the equation, and we can divide by x, and there we have our expression for dy dx. It comes right out. I notice over here we had minus 1 over x squared, but y, that's 1 over x, so this is the equivalent to minus 1 over x squared. What we wanted to do, though, was take a simple example as to how we can use implicit differentiation when we have the product of two variables. So, with that in mind, let's take a more complicated example. Suppose we have, say, x squared plus 2x times y plus 3 times y squared equals 4. And we want to solve this for dy dx. So we go along, this here would be 2x, and we'll go ahead and write it down, 2x dx plus, now here we would have, here's a product of two variables, so we would have 2 times y times this derivative plus 2 times x times this derivative. Okay, so we have 2 times y times this derivative, that's just dx plus 2 times x times this derivative, that's dy dx, plus 6y, 6 times y consists of the 2 minus 1 power, dy dx, don't forget to take your derivatives, equals the derivative of this, which is 0. Okay, and this dx, that's 1, that's 1. We put them in there just to remind ourselves. And here we have dy dx equals 0. And it looks like we can divide both sides of the equation by 2, so that's 1, that's 1, that's 1, this will be 3. So what do we have? dy dx times x plus 3, and then on this side of the equation we have plus x plus y. And that is supposed to equal 0. So take this over to this side, and we can say minus x plus y, because that'll be minus x minus y, and divide it by this, and there is dy dx. So dy dx, we got a little bit neater over here, dy dx equals negative x plus y divided by x plus 3. So for this equation here, this is what dy dx is. And again, it's probably in a different form than what you've been used to seeing. And the reason for it is, back here in our original equation, you see, y is just one of the variables here in this general equation. Before, when you were solving problems, we were saying that y is equal to something times x to the something else power plus x to a different power, and so forth. We stated explicitly what y is equal to. Here, we don't have that situation, but we can still differentiate, like we went through the whole process here, and we can still determine, without too much problem, what dy dx is equal to. We're just getting a different kind of expression for it than what we've been used to seeing when we solved these kind of problems in the past. But it's not a hard technique, and it's a very handy one to use when you have these more complicated kind of equations. But that's it for this video. Come back and join us for the next video, and again, we're going to tackle an implicit differentiation for a bit more of a complicated problem.